I once heard a great question posited on the internet, and it was, which state has a longer coastline, Maine or California? And I think it's a great question because it is completely paradoxical. The answer is absolutely paradoxical, and it really illustrates exactly what we need to talk about in this section. So, if Google doesn't mind here, and I didn't ask them permission, I'm going to use a great little tool they have to measure distances. And I'm not going to compare the distances of the coastlines of California and Maine. I really just want to focus in on Maine so that we can kind of get an idea of what we're doing in this section. So, if we're very far zoomed out and we want to calculate the coastline of Maine, it looks, based off of this tool, roughly 220 miles. Okay? But the thing is, if you notice here, you can kind of see there's some blue that bumps in a little bit, and that kind of tells you that you're not actually measuring the actual coastline here. You might have a lot of error in your measurement. So if you were to use, instead of just the straight line distance from one side of Maine to the other, perhaps you could get a better estimate, which would sort of require us to zoom in a bit. So let's zoom in on this coastline. Okay, so now we can tell we've definitely missed the mark quite a bit. All right, this point looks fairly okay to me, but this actually is landing in Canada. So let's bring that point over here. Now, you can definitely see that a lot of my estimate is basically just over water at this point. So if I am actually wanting to measure coastline, I need to remap this and basically use a smaller ruler, for instance, and try and match the coastline as best as I can. Now, in doing so, I will get a better approximation. All right, now I'll try and just do this quickly here as best I can. And clearly this is going to increase the approximation. So we're at, what do we have now here? Why does that say 0? Is that the start? Yes, okay, so for some reason it reversed. All right, so now it's 307, so slightly longer. But that's at this level of zoom. I can actually zoom in even further. Okay, and here's a little place where I could do a better job of getting an estimate there, and I could do this all day. Like, I could really do this for a long time, and I'm not going to, if you're wondering. All right, but the thing is, then you have the question about, like, what to do with all these islands, like, and these inlet rivers. Like, how far should you go in the inlet river? Like, technically, something that is coastal is going to exist next to water. So you could really call any of these islands up here coast, and you could, whoops, messed that up. And you could measure around the islands. You could measure, get better and better approximations. You could go into these rivers, and like, there's just a lot that you could actually do to increase the level of accuracy of this measurement. I think it works out to there's something like 1,200 miles of coastland if you do this and take into account all the river, all the islands and whatnot. Not important for this lesson. What is important is that if you are trying to figure out the distance between 2 points, you can get a better and better approximation by doing subintervals. Similar to is if we were wanting to do the same for, say, a function. All right, here I have a mathematical function, and I've plotted it here. And it doesn't really matter what this function is, I just have a graph of it. And I want to figure out what the arc length is. And the arc length I'm defining as the distance along the curve from one point to the next. Now, it really depends on how many subintervals I use as to how good that approximation is. So, for instance, right now I'm using one subinterval, and the approximate arc length is 5 units. It's definitely not a very good approximation because this line does not follow my curve really at all. But let's say I split this into 2 subintervals. Okay. If I do that, now I have a little bit better. The approximation went up considerably to 7.4, but I'm still not really following my curve all that much. If I break it into 3 subintervals that are equal length, well, now I have 3 points along my interval, and I have an arc length of approximately 15. If I go and do 4 subintervals, I'm getting a better and better approximation. This part right through here hugs the curve pretty well. We deviate quite a bit this way and here, but now we're starting to get a fairly decent approximation with 4 subintervals. The more subintervals that we do, the better and better our approximation is going to be. And you can see that with the arc length. So the arc length does improve with each new level of subintervals, but it starts not improving all that much. We're starting to limit to an actual value here. And if I let the number of subintervals increase to infinity, then basically I would get the actual length of the curve. Now, how would I go about making these approximations? Well, starting from here, this is just the linear distance between these 2 points. So that's fairly straightforward. But if I break into 2 subintervals, I basically have split this interval in half, use the start, the midpoint, and the end point, and I can calculate the 2-dimensional distance between these 2 points. And when I say the 2-dimensional distance, I'm not talking about just subtracting 2 values like in 1-dimensional distance. I'm talking about the distance formula. So d equals the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. I can get that distance between these 2 points, that distance between these 2 points, add it together. That's where this approximation is coming from. If I split into 3 subintervals, I have 3 points, and I can calculate the height of the curve at each of those points, and then calculate the distance between those points 3 times, and then add those distances together. And that's how I am going about determining the approximate arc length. Now, because this is running into a limit, there's probably a way that we could work some calculus into this. So for the next portion of this, let's take a look at how we can do that. Okay, so we saw in the introduction how if we're trying to find the arc length of some curve, and we'll just call this curve f of x, and we want to calculate the arc length between 2 points, so A and B, then what we learned is the straight line distance between A and B gives a really poor approximation. All right, so if I just calculate the distance between these 2 points, and of course this point is A f of A, and this point is B f of B. If I want to actually come up with the distance between there, I can use the distance formula, and the distance formula is, of course, d equals the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And since we have an x and a y value for these 2 points, we could do this by simply taking, say, the distance here would be the square root of b minus a squared minus, plus f of b minus f of a quantity squared, and that would all be underneath that square root. I just ran out of space there. Okay, so that's how we would get the first approximation. But if we split this up into subintervals, and let's say we did a few intervals, like split it up into 4 subintervals, then at that point we would follow along the curve this way, and we could get the distance on each subinterval So I'll call this D1, D2, D3, and D4. We add those together, that would give us a better approximation. So using subintervals will get us better approximations. So let me just say this is x1, x2, x3, and then we would have points where we could get the coordinates of these points along the curve using the function itself, add together. Okay. Now, we also discussed saying that if we took a limit as the distance between these points goes to 0, we would actually get the exact distance along the curve. So let's work on something of that nature. To do that, it might be helpful to zoom in on a subinterval. Okay, so for instance, if I have just some general curve like this, and this is, say, some x value along our subinterval, which I'll call x sub I, and this is the next in line, so x sub I plus 1. And what we would be looking for is this distance from here to here, which would be the approximate arc length on that ith subinterval. So I'm going to call that s sub I. Now these points we could definitely determine because we know the x value and we know our function, so we would just place that x value into our function to get those points. Although the notation gets a bit crazy here, but that's what it would look like. And what I could do then is I could say the arc length on this ith subinterval is the square root of x sub I plus 1 minus x sub I quantity squared plus y sub I plus 1 minus y sub I quantity squared, taking into account that the y value comes from the function. Okay? Now, let's see. So the next thing I could observe here is that the distance between these 2 points here is what is known as delta x. And delta x is, of course, going to be the difference between any 2 endpoints of subintervals. So x sub I plus 1 minus x sub I, which is exactly what I have right here. So I could really simplify this and just say this is the square root of delta x squared. And then I can do the same over here as well. I didn't really leave myself a lot of room for delta y because like this would be y sub I, and not much lower than that is y sub I plus 1. But the difference between those two is still known as delta y. So let's write that in as delta y squared. Okay. This is going to calculate just the arc length on this subinterval, but I think there's some things we can do with this algebraically. So for instance, I'm going to start off by multiplying this by delta x over delta x. And I can actually bring this underneath the square root so long as I make this, squared. So this would become times delta x squared over delta x squared. And when I say delta x squared, I'm meaning this. So it's, the delta is part of the variable name, okay? So I'm meaning the whole value squared. Now, in doing so, I could actually multiply this into this set of parentheses and simplify some things. But I'm not going to multiply both terms. I'm just going to multiply the denominator one. So I'll leave the delta x squared from the numerator out front, and then I will make this delta x squared over delta x squared plus delta y squared over delta x squared. Okay, so I took the one in the denominator, distributed it into these parentheses, which allows me to manipulate some more things. Delta x over itself divides and becomes 1. So this would be delta x squared times 1 plus, then I have this, which I can rearrange and call delta y over delta x quantity squared, because whenever you square a fraction, it's the same thing as just squaring the numerator and denominator separately. Now this delta x squared on the outside could be factored out, and I could write this as delta x times 1 plus delta y over delta x quantity squared. Okay, now as we let delta x go to 0, some interesting things will happen here. All right, if we let delta x go to 0 and we take a limit, the thing that will happen here is, a limit, I wanted to go ahead and just take the sum of all these. So a limit of the sum of all the subintervals here's what we would get. So the total arc length then, and this would be the exact arc length, this would be the limit as delta x goes to 0 of the sum of all of these things here. So delta x times the square root of 1 plus delta y over delta x quantity squared. So when we take the limit of a sum with respect to some variable delta x, you might recall this as the basic definition of an integral, and it is. So it would be an integral from a to b, and we would be integrating dx, but we would be integrating this function right here. And this function is kind of interesting too. It is a square root, but it's the square root of 1 plus delta y over delta x quantity squared. Delta y over delta x, that should, as we take a limit, will turn into dy dx, which is the derivative of our function. So we can actually write this as f prime of x quantity squared. So we're squaring the entire function here. And that is how we could come up with the exact arc length of a function on a subinterval. So theorem states here, let f of x be a smooth function over the interval a to b, and the arc length of the portion of the graph of f of x from the point a f of a to b f of b is given by this function right here. Now, there can't be any discontinuities or points that are not differentiable, so we say that this has to be a smooth curve, and a smooth function is just one whose first derivative is continuous, so there's no holes in the graph, no asymptotes, or any sharp corners. So those would be all places where we could not take a derivative. All right, let's try it out. So let's approximate the length of the graph of f of x equals x cubed plus x squared minus 10x plus 8 on the interval from 1 to 3. We're going to round the answer to 3 decimal places. Now, first off, just so you know, whenever you see the word approximate, that tells you that it's perfectly okay to give your answer as a decimal value. And a lot of times why that is because there's just no way to get an actual exact answer for some of these integrals. As nice as the theory is here for this arc length formula, the problem is this runs into an integral that is very often just not integrable. Square roots are very difficult functions to work with and integrate to get an exact answer, that is. So a lot of times we just have to rely on approximation methods. And there are some functions out there which, when you take their derivatives, you can get an an exact answer. But that leaves us with like 2 or 3 examples that we could possibly work here. So in order to not worry about the type of function that we would do, we're just going to approximate our answers using fn end. Okay, so let's see how this would work. Now, we really don't even need to see the function. As long as we know it's a smooth curve, everything's fine. So the arc length here, we would integrate on the x interval from 1 to 3 of the square root of 1 plus f prime of x quantity squared dx. So we need to figure out what f prime of x is. So the first derivative of this function would be 3x squared plus 2x minus 10. And that would go into this arc length formula. So the integral from 1 to 3, the square root of 1 plus 3x squared plus 2x minus 10 quantity squared dx. Now, you don't need to multiply this out. You could, and you could add to 1, but it's not going to help f and int work any better or worse. So, to be honest, just get to this point right here, and then we'll use f and int to get our answer. So, we're integrating this function from 1 to 3, and it is the square root of 1 plus, in parentheses, 3x squared. Oh, I'm still in that t thing. Let me switch the mode to function. It doesn't really make a lot of difference, but I kind of prefer. There we go. 3x squared plus 2x minus 10. And that set of parentheses is squared. And then we're integrating dx. So 17.0, well, to 3 decimals, we'll say 17.060. And there we have it. The next example is not really much more difficult. It might look like it because we have a function that is written in terms of the variable y instead of the terms x, instead of the variable x, but that's okay. We're still doing the same thing. We are going to approximate a solution in the end, so we're fine to use fn int. You might want to draw a graph just so you can get your bearings straight as to exactly how this will work out. 3y squared, that would effectively be a parabola, but it's going to be facing this direction instead of up. So it might look something like that. Then we would be integrating over the interval from 1 to 2, and it's important to note that because our the function is defined of the variable y, this is a y interval. So where y is equal to 1 to y is equal to 2, that would be from here to, say, right here. So this is the arc length that we actually want to calculate. That would be calculated s equals the integral from 1 to 2. And then, of course, the square root of 1 plus g prime of y, quantity squared, dy. Since everything's of y, we need to leave our function of y, and that's no problem. The derivative of the function g could be found just using standard rules here, so 6y. So my arc length formula here then would become the integral from 1 to 2 of the square root of 1 plus 6y quantity squared dy, which you could leave as is, or if you wanted to make it like this, just to make it easier to type in, so 36y squared, that's fine. We'll just then use fn ent at that point, so math 9, we want the integral from 1 to 2 of the square root of 1 plus 36 x squared dx, which looks like results in 9.058 into 3 decimal places.